Constructed in 1926 under Sir Harcourt Butler, the weir became a cornerstone of the Ganga Canal system, supplying water to thousands of hectares of farmland and supporting the region's growth for nearly a century. After nearly a century of service, the Bhakra Weir had reached a critical stage of deterioration. The gates were outdated, prone to leaks, and difficult to operate. Downstream apron slabs were broken and large cracks had developed in the main structure. These vulnerabilities not only reduced the irrigation potential, but also posed serious risks during floods, when timely gate operation was essential to prevent damage and maintain water storage. The old falling shutter gates relied entirely on manual operation. Any delay in opening during sudden floods, a common occurrence due to the catchment's steep topography, posed a serious threat to the entire structure. Operating the gates in such conditions was extremely dangerous, often putting lives at risk, as seen in this footage. If the gates were not closed in time after a flood, the FRL could not be restored, leaving storage dependent solely on post-monsoon rainfall. The gate's structural elements were always vulnerable, and in many instances, entire gates were washed away, causing a complete loss of ponding until replacements were installed. Leakages from the gates were found to be excessive, compromising efficiency, and as a result, the canal system's full irrigation potential was never achieved. These are top-hinged, self-operating, non-submersible, hydromechanical gates that open and close automatically, without the need for electrical power or manpower. They regulate outflow in direct response to the upstream water level, deciding when to open, how much to open, and for how long to remain open. For added flexibility, they can also be operated manually in controlled mode to release water for environmental discharges or dam safety purposes. These gates have been favorably mentioned in iCold Bulletin, recognized by leading engineers worldwide and also included in various international publications. They are considered highly reliable, very safe, and a quantum leap in hydromechanical gate technology, outperforming conventional gate systems. The gates are currently in closed position and remain closed until the upstream water level reaches the full reservoir level, thereby ensuring maximum storage. About 25% of the gates are designed to allow a thin overflow, around 100 millimeters. This lets debris, flotsam, and aquatic weeds pass without requiring gate operation. This feature is optional and can be excluded, as per the preference. Other gates have additional baffle plates which prevent overflow while providing additional hydraulic thrust, ensuring smooth and reliable gate opening. As the upstream water level rises further, hydraulic pressure pushes the gates outward and upward, initiating the opening. With further rise, they open progressively wider while floating above the water surface. At high flood level, the gates reach their fully open position, discharging water completely unobstructed, operating just like an ungated structure. The gates open sequentially, not simultaneously. Each gate responds to a 50 to 100 millimeter rise in level, allowing controlled release of initial floods and preventing unnecessary full gate operation during minor floods. When the water level recedes, the gates rotate downward and inward, closing gradually. They fully shut once the reservoir returns to FRL, ensuring reliable storage. With no motors, sensors, oiling, or greasing required, the system is virtually maintenance-free, a true fit-it-and-forget-it solution. The execution plan covered every phase: survey, design, surface preparation, installations, and testings. By applying specialized techniques, the existing masonry weir was upgraded to meet modern demands, built for the future. The project began with a detailed site assessment and survey, capturing structural conditions, hydraulic parameters, and topographical data, the foundation for precise design and execution. Site preparations included construction of the approach road, building of the cofferdam, and execution of dewatering to ensure safe working conditions, along with mobilizing all tools, machinery, and equipment required for execution. Existing piers were cut using the highly specialized diamond wire sawing technique, a non-destructive, vibrationless method that prevents any crack formation in the existing structure. This technology offers several key advantages. It is non-destructive, ensuring the original structure remains unharmed. It is completely vibration-free, avoiding stress on surrounding materials. It delivers high-precision cuts for accurate execution. And most importantly, it maintains the structural integrity of the century-old weir while enabling modern upgrades. Diamond core cutting was used to drill precise holes in the existing weir structure. This high-accuracy, non-destructive method ensured clean cuts without damaging the surrounding masonry, allowing for secure installation of dowel bars. Surface preparation involved thorough cleaning of the existing structure to remove silt, biofilm, algae, and mineral deposits. High-tech equipment, including powerful water jet systems and electrical buffing machines, ensured a spotless finish without streaks or patches, creating the ideal surface for the next stage of work. 2.5 meter long, 8.8 grade, zinc-coated, fully threaded dowel bars were grouted into the structure using non-shrinkage cementitious grout. This provided a secure, monolithic bond between the century-old masonry and the newly constructed concrete elements. It further ensured effective shear resistance and reliable load transfer. A high-performance epoxy-based two-component resin system was applied to the surface of the existing masonry, penetrating its pores to create an exceptionally strong adhesive layer. The bond acts as a barrier coat and its strength is greater than tensile strength of good quality concrete, ensuring a seamless monolithic bond with the newly cast M20 RCC jacketing, enabling the old and new structures to act as a single, unified body. The result was a significant enhancement in structural strength, durability, and resistance to future environmental stresses. Deep scour pits had formed downstream of the weir, posing a potential threat to its stability. The area was first dewatered, followed by careful removal of all loose material and side dressing to stabilize the edges. Multiple graded filter layers were laid to prevent future erosion, topped with plain cement concrete for a solid base. And finally, reinforced cement concrete was placed to provide long-term structural protection. The gates arrived on site, transported on heavy trailers, and were carefully unloaded using 2 hydraulic cranes. They were then shifted into their staging position, ready for the next phase of lifting. Before installation, each gate underwent a detailed inspection by the executive engineer along with the SDO and junior engineer to ensure it met all specifications. From the bridge, positioned high above the base, an 80-ton crane lifted the automatic gates and placed them near the installation points. Pivot arms were then mounted onto the trunnions with precision, followed by the careful hoisting of the gates into their final positions. With all adjustments complete and precise alignment achieved, a crucial factor for reliable gate performance, the installation of the gates was successfully finished, marking a key milestone in the modernization project. The inspection bridge was installed to provide access for operational inspection and manual operations for environmental discharges. Precise alignment and leveling were carried out to ensure structural stability, which is critical for operational safety.